Imagine you are 37,000 feet above the North Atlantic, suspended in darkness, traveling at 550 miles per hour, and the only thing telling you exactly where you are, a small box bolted to the ceiling of the flight deck, goes silent. Not broken, not malfunctioning, simply gone. Every aircraft in the sky at that moment faces the same problem simultaneously. And the question the world has never seriously stopped to ask is this: what happens next? GPS has become so embedded in modern aviation that the industry rarely discusses what it would look like without it. That invisibility is, in itself, the danger. And if you find yourself fascinated by the hidden systems that quietly hold modern aviation together, the ones nobody talks about until they fail, consider subscribing, because this channel exists to explore exactly those invisible vulnerabilities. For most passengers, GPS is a convenience, a moving map on the seatback screen that tells you there are 4 hours and 12 minutes until touchdown. For pilots, dispatchers, air traffic controllers, and the engineers who built the global airways system, GPS is something far more structural than that. It is the invisible spine of modern flight. And like most spines, its true importance only becomes apparent when something goes catastrophically wrong with it. To understand what a 24-hour GPS outage would actually mean for aviation, you have to understand how completely the industry has reorganized itself around a signal that comes from space. The GPS network, formerly known as the Global Positioning System, is a constellation of at least 24 operational satellites maintained by the United States Department of Defense. These satellites orbit at roughly 12,500 miles above Earth, each broadcasting a continuous timing signal. Receivers on the ground or in an aircraft collect signals from multiple satellites simultaneously and use the tiny differences in arrival time to triangulate a precise position, accurate to within a few meters. That precision, delivered continuously, transformed aviation in ways that would have seemed like science fiction to the generation of navigators who flew with paper charts and stopwatches. Before GPS became operationally dominant in the 1990s and 2000s, commercial aviation relied on a patchwork of systems that were expensive, geographically limited, and often surprisingly imprecise. Inertial navigation systems, or INS, used gyroscopes and accelerometers to estimate position by mathematically tracking every acceleration since the last known point. They were extraordinary engineering achievements, and they drifted. On a long oceanic crossing, an INS could accumulate an error of several nautical miles per hour of flight, meaning a 12-hour transoceanic route might place the aircraft several dozen miles from where the system believed it to be. That sounds alarming, but oceanic tracks were designed with wide lateral separation specifically to accommodate this uncertainty. The sky was organized around the limitations of the tools. Then came GPS, and the sky reorganized itself around precision. Oceanic separation standards were reduced because aircraft could now be tracked and positioned with extraordinary accuracy. Airports built approaches that guide aircraft down narrow electronic paths to runways in near-zero visibility, paths that depend entirely on GPS signals to define their geometry. Air traffic control systems in dozens of countries were redesigned to process GPS-derived data as their primary positional input. The efficiency gains were enormous. Airlines saved billions of dollars in fuel by flying more direct routes. Runways that were previously unusable in fog became accessible. The system became tighter, faster, more dependent, and more fragile. A 24-hour outage would not begin with chaos. It would begin with procedure. Every modern commercial aircraft carries backup navigation systems, inertial reference units, VOR receivers that pick up ground-based radio beacons, and DME equipment that measures distance from ground stations. Pilots train for GPS failures. The procedures exist. What the procedures were not designed for is a simultaneous, global, 24-hour loss affecting every aircraft and every airport on the planet at the same time. The first consequence would be invisible to passengers. Within minutes of a confirmed outage, airlines and air traffic control agencies would begin routing aircraft away from GPS-dependent approaches and GPS-only waypoints. Oceanic tracks, those carefully spaced corridors over the Atlantic and Pacific where there are no radar systems and GPS is the primary means of separation assurance, would immediately require wider spacing. This means fewer aircraft can fly the ocean simultaneously. The transatlantic corridor, which on a peak evening moves roughly 400 to 500 flights in organized waves, would have its capacity cut significantly. Flights would be delayed, rerouted, or canceled. Within the first few hours, the cascading effects would reach the ground. Airports that rely primarily on GPS-based approach procedures, and there are hundreds of them, particularly smaller regional airports that lack the infrastructure for older instrument landing systems, would effectively close in poor weather. The ILS, or Instrument Landing System, is a ground-based radio guidance technology that predates GPS by decades and remains the gold standard for precision approaches. But ILS requires significant physical infrastructure. Not every runway has it. Not every airport can afford it. GPS approaches were partly adopted because they were cheaper to implement and required no ground equipment at all. In a sudden outage, those airports become weather-dependent in a way they haven't been for years. The North Atlantic is perhaps the most acute pressure point. Every night, hundreds of aircraft cross it in organized tracks from Europe to North America. ATC agencies in Shanwick and Gander, controlling vast swaths of the ocean, have no radar coverage. They manage separation using position reports, timing, and GPS-derived data. Without GPS, aircraft would revert to procedural separation. Larger distances, slower traffic flow, fewer tracks usable simultaneously. Airlines trying to launch evening transatlantic departures from London or Paris would face significant holding delays while controllers rebuilt the traffic flow around degraded capability. Some flights would simply not go. What is striking about this scenario is not the drama of it, but the mundanity. Aircraft would not fall from the sky. Pilots are trained. Systems have backups. What would happen instead is a profound economy-wide friction, a grinding slowdown of the global air transport system that would feel, from the outside, like a bad weather day everywhere on Earth at once. And here is something worth pausing on. Do you think aviation is too dependent on a single space-based signal, or is this simply the price of efficiency? I'm genuinely curious how you see that trade-off. Let me know in the comments. Thousands of flights delayed, hundreds canceled, passengers stranded at regional airports that quietly lost instrument approach capability. Air cargo, the circulatory system of global manufacturing supply chains, disrupted in ways that ripple through industries that have nothing obvious to do with aviation. And here is the deeper, stranger truth that the outage would reveal. The aviation industry knows this vulnerability exists, has known it for years, and has made a conscious, rational, economically logical decision to accept the risk in exchange for the efficiency gains GPS provides. This is not negligence. It is a calculated trade-off made by engineers, regulators, and airline executives who understand that no system is without risk, and that the alternative, maintaining full parallel infrastructure for a pre-GPS world indefinitely, is financially impossible. The lesson GPS dependency teaches is not that aviation made a mistake. It is that every technological revolution in aviation has always involved accepting new categories of risk while eliminating old ones. The introduction of jet engines brought new failure modes. Fly-by-wire systems removed mechanical linkages and replaced them with software. Each transition narrowed some risks and opened others. GPS narrowed the risk of positional uncertainty and expanded the risk of systemic dependency on a single signal architecture controlled by a single government. The answer to what happens if GPS stops working for 24 hours is, ultimately, this. Aviation survives, adapts, and manages. But not without cost, not without disruption, and not without revealing how completely the modern sky has been built around a technology most passengers have never once thought about. That is the quiet genius and the quiet vulnerability of the invisible spine. You never notice it until it's gone. And in aviation, the things you never notice are always the ones that matter most.